Hello everyone, I'm Po Junxie. I'm in MatSE504 Solid State Materials, lectured by Professor Stephanie Law. And in today's video, I would like to show you a very powerful software in the study of crystal materials, which is VESTA. And I will use this software to try to explain some of the usually confusing concept in crystal materials. As we can see here, is developed by a team in Japan, which is by Koichi Mona and Fujio Izumi. And here is its reference and how to cite this software. In Vista, usually you import a CIF file, and CIF is crystallographic information file. Yeah, and for example, there's another very powerful website, which is Materials Project. I believe a lot of people have already known this website, and yeah, this website record many reported materials and its property and its crystal structure. So here, for example, let's see, I want to know more about the crystal structure for iron. Okay, search for iron. Yeah, you can see. So this one is the body center iron. I believe it is ferrite, right? Yeah, it is ferrite. And here, of course, you can see its structure here and some of the information of its crystal structure and a lot more its properties. But today, I'm going to focus that we can download its CIF file here. Save it. Okay. So first of all, what is a crystal material? So in the lecture, we always hear a lot of confusing terminology like crystal system, unicell, lattice. Are they the same thing or are they different concept? Yeah, they are very easily to be confused between. So basically, crystal material is a material that is consist of repeating in an order arrangement of atoms. So there are limited ways to arrange these atoms, which is these 14 Brevis lattice. So so far, all materials can be found arranged. All the solid state materials can be found arranged in these 14 Brevis lattice. So in total, we have 14 ways to arrange the atoms here. And these 14 Brevis lattice can be characterized into 7 lattice systems. So you can see that we have iron atoms in each corner of this cubic, and we also have another iron atom in the center of this cubic. However, actually, all of these iron atoms you see here, they are equivalent. What it means for equivalent? It means you cannot differentiate between them. Or you may say that, yeah, it's clearly that this iron is in the corner, and this iron is in the center of the cubic. How couldn't I differentiate between them, right? So we have to look at a bigger picture. So I can make the repeating units more here. Okay, let's show. Okay, so in the real life, actually, we are seeing iron crystal like this and even have more repeating units, right? Yeah, we have nearly infinity atoms in the real life. Okay, so in this case, you might still say that, oh, it's very clear, like this iron is at the corner of the cubic, and this iron is in the center of the cubic, right? No, but actually they are the same. So if I turn off the unit cell line here, and let us look more closely. So yeah, can you differentiate between which atom is in the corner and which atom is in the center now? Is no, no, they all look the same. So if we look closely to the down left corner here, we can see the body center unit cell we saw before, right? So like these four atoms are the atoms at the corner of the cubic, and this atom was the atom at the center of the cubic, right? You may still think it that way, but if we look closely to another region, yeah. So we look at here, and this iron atom, and this one, and this one. These four iron atoms can be the atoms at the corner of a cubic now, and these atoms become the atom at the center of the cubic. See? So another way to look at equivalent is that, for example, we look at this atom, okay, and let's remember how it looks now. Okay, it looks like this, right? And then I move my focus to another atom. Okay, I look at this iron now, and you will realize that it is impossible for us to differentiate between them. For this atom and this atom, they are different atoms, right? But now, can you differentiate the difference between them? No, they look totally the same. So that's why we call it equivalent. Okay, so now let's move to a more complex example, which is silicon crystal. So as you can see that it is a silicon crystal here, and it is very difficult for us to tell what's the crystal structure of it. And you may say, oh, I see crystal here, silicon atom here, 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 here. Okay, so what is this? Yeah. So is it cubic? Is it oh no. Yeah. So we cannot tell the crystal structure of this crystal in that way, actually. And it will be even more difficult for us if we cannot see the unit cell line and looking at the bigger picture, right? But this is how a crystal looks like in real life. So how do we do that? First of all, let's find the equivalent point of this crystal, because the lattice is the arrangement of equivalent point. So if we can find the equivalent point, then we can see how they arranged, and then we can determine its crystal. So let's see. So we see silicon here, and we see another silicon here. Are they equivalent point? Are they? No, they are not. Why? Because they are very different, right? So if we look at this atom, yeah, look at this atom and compare it to this atom. You can easily tell the difference. The bonding angle are different, right? So, because we can easily tell the difference between them, they are not equivalent point. On the other hand, if I'm looking at another silicon here, let's look at it, and compare it to this silicon atom. Can you tell the difference between them? No, they look totally the same. So what does it mean? It means these two silicon are equivalent points. So let's highlight them. This one and this one. And let's find out more. So this one is actually also equivalent to them. And let's see. Also this one and this one, right? They all look the same. We cannot differentiate between them. And after that, if we rotate the crystal, we can find out that they're actually lining on the same plane. So actually, the crystal structure of silicon crystal is a face center cubic crystal. Now we can do this process in another phase here. And another phase here. And then we can find out that, oh, it is actually a face center cubic. So I mentioned that we have two different types of silicon in silicon crystal. And I also showed you that the equivalent point of crystal structure of silicon is arranged in the manner of face center cubic, right? So actually, the crystal of silicon is composed of these two types of silicon arranged at each equivalent point of the face center cubic. So in order to show that, I'm going to color all the other types of silicon in red to better show that. Okay, so we can see that if you look at these two silicon, they lining at the down left corner here, right? And we look at this pair of silicon, they are lining at the center of this face. And we look at these two, they are lining at the down right. And here, how about this? We cannot see the silicon peering to it, right? Right? So it's actually there, just we are not showing it. Let's increase the scope. We are looking at this crystal. Yeah. And we can see it here, right? And this one also. Even if we rotate a little bit to see the other end, you can see that these 5 silicon also arranged in the same manner, right? Here is one red silicon in that direction, peering to it. That. So we can say that it is these two type of silicon atoms arranged in the order of face center cubic to form the crystal structure of silicon. So as I have shown, that VESTA is a very powerful software in the study of crystallography. So I believe it will be very helpful for you if you can play around with the software yourself. So thank you very much.